current from the capacitor is given by IC is equal to IL minus I naught. This is IC, this is IL, and this is I naught. So IC is equal to IL minus I naught. Therefore the current shape should be triangular. Why? Because the waveform from the inductor was triangular in shape and we are subtracting a DC level from it, so the waveform is only shifting upward or downward and the shape will still be the triangular. So the time from here to here is T by 4, and then for this time is T by 4, then this time period is T by 4, and then from here to here this is T by 4. So the time corresponding to this triangle, this will be T by 4 into 2, which is equal to T by 2. The charges can be, the charges deposited on this capacitor can be given by Q is equal to CV. The area of this triangle can be calculated as base multiplied by T by 2, base multiplied by its height, delta IL by 2. This complete ripple is delta IL, and the half on this upper side is delta IL by 2. So C delta V is equal to delta IL over 8F. Okay, so now put any of the value of delta IL over here, either that we calculated in terms of V naught or that we calculated in terms of Vs. So by putting any of those values, the end result will be something like this. In terms of Vs we will get this expression, and in terms of V naught we will get this expression. Delta V naught is equal to 1 minus K into V naught over 8F square LC. So the ripple in output is inversely proportional to the square of the switching frequency and to the sizes of this inductor and capacitance. And so we have already calculated the value of this inductor. So depending on whether we are which of these is known, either delta V or capacitance, so whichever either one will be known, so we can calculate the other quantity. Either we can calculate the capacitance or we can calculate the ripple in output voltage. And then this is another manipulation. Delta V is equal to 2 V naught. So if this is the maximum ripple in my output, if I consider this is the maximum ripple that can appear in my output, so I will just use this value over here, and this will be the critical value of capacitance that I can obtain. So once you have known this value, then all of the other expressions can be easily calculated, irrespective of the fact whatever the value of this ripple is, either it's 2 V naught, 3 V naught, or whatever. So this expression is important to that either you remember it or you know how to derive it. So the understanding of this formula is important. Now it is also very important to calculate the rating of this inductor, capacitor, not capacitor, the inductor, the switch, and the diode, as we calculated in the in our rectifiers as well. So it is important that we know about the rating of our elements in circuit as well. So if you look at the circuit diagram, so the current from the switch only flows when the switch is on. The supply, Vs, and switch are only operating during the first mode. When the switch will be on, so that is the only time during which the supply will be in my circuit. During the mode 2,
when this switch will be in off state, in that case this supply will have no path. You can see here that the switch is open and the current cannot be supplied by this supply in that case. Since the switch and supply are both in operation when the during the mode 1 when the switch is on, therefore the current from the supply, the average value of the current from the supply is equal to the average value of the current from the switch. Also see over here that this is my supply voltage. It is only available at output from 0 to kT time period, and this is the time period during which the inductor is charging, and this same current is flowing from the switch because switch is in series with that inductor, and the same current is flowing from both of them. After this kT time period, when the switch is in off condition, so when this switch is in off condition, in that case the energy from this inductor will freewheel through this diode and will be supplied to the load. So the current from this diode shape should be similar to the discharging shape of the inductor. If this is the shape from the inductor, this is the rising slope during the charging, and this is the negative slope during the, or decreasing slope during the discharging time. This part of the this part will be due to the switch, and this is due to the diode. Because this is during the mode 1 when switch is charging, when the inductor is charging, and the current is only flowing from this switch, and this is during the mode 2 in which the current is followed is being the path for this current is provided by this diode. So from switch it is a rising slope, and from diode the inductor is discharging, so the slope from the or the current shape from the diode will be like this. If there are no dissipating element in my circuit, that is, I consider the circuit to be ideal, that is no drop across the switch, and we have already said that the inductor, the average value of voltage across the inductor is 0, and there is no drop across the inductor. Therefore the input power and output power should be equal to each other. VSIS, supply voltage into switch voltage, supply voltage into supply current, is equal to V0 I0, output voltage into output current, and output voltage V0 has expression for this V0 is already derived, which is kVs. Using that value over here, so the average value of the current that is being drawn from the supply is K times I0. I0 current is available at output throughout the time period, but the current at output due to the supply was only for k percent of the duty cycle when the switch was on, and we have discussed that the switch is only operating when the supply is in operation in my circuit. Therefore the average value of the switch and supply is same, so IS average is equal to I switch average, and it is equal to K times I0. And now the peak value of the current from the switch is equal to average value of the current that is flowing from the switch plus this ripple delta IL by 2. So see if this is the average value of the current flowing from the inductor or from the switch. In that case this is basically the ripple, the peak value delta IL by 2, that is flowing from the inductor, and inductor and switch are in series in mode 1, So same ripple should follow from the switch as well. Therefore this ripple is also appearing in the current waveform of the switch. The peak value of the current from switch is equal to IS average. Okay, so supply and switch current are both same, so I can either call it now the switch current or supply current. So the peak value of current from switch is equal to average value of current from switch plus this ripple, and RMS value can be calculated like this. In our LC filter as well, we saw that we had a constant DC level and an AC ripple over it. In that case, we said that the RMS of such a waveform can be calculated by taking the DC value square plus whatever the RMS value of the second of that ripple is. In that case, it was sinusoidal, so we used delta IL, I mean peak delta IL by under root 2. But now here the peak is delta IL by 2. If this is my total ripple delta IL, so this is delta IL by 2, this peak. So delta IL by 2 is peak divided by square root 3. This square root 3, the RMS value of a triangular waveform can be calculated like this: the peak value divided by square root 3. So this is a triangle in shape, therefore the RMS value is will be calculated like this.
Now it's time to calculate the diode current. So the current from diode only flows when the switch is off, and if the switch is on for k% of the cycle, then it is off for the 1 minus k cycle. So ID average value can be calculated as the time, the percentage of the duty cycle for which the current will be flowing from this diode, and the time and the duty cycle is 1 minus k, that is the off time. When the switch is off, then the current is flowing from this diode, that is why 1 minus k into I naught. You see over here in this case, the switch from the current from the supply and the switch was only flowing when the switch was on, and the switch was on for a duty cycle k. So the average value of the current from the switch was k times I naught, and here the current from the diode is flowing when the switch is off, and switch is off for 1 minus k time period. So 1 minus k into I naught. From this I will get the ID average. Now ID average is the peak value k is similar to that that we calculated for the switch. The current waveform from diode will be something like